Okay, I think I'd like to get started. So I'm James Allen. I'm the director of the Center for Intelligent Information Retrieval. Welcome to the CIIR talk for December. So today I'm delighted to introduce Franco Maria Nardini, who is the research director with ISTI-CNR in Pisa, Italy. That's the one with the leaning tower, or one of the ones with the leaning tower. His research focuses on web information retrieval and also on machine learning / deep learning. He has been an author or is an author on more than 100 papers, so very active in the field. He has served as general co-chair of ECIR 2025. Being general chair of a conference is an incredible service contribution to the community. And so if you ever see him, thank him, even if you weren't there. He has been the program committee co-chair of Spire 2023 and the tutorial co-chair of Wisdom 2021. So which are also both substantial service contributions. He is the co-recipient of the ECR 2025 Best Student Short Paper Award, presumably co-recipient because he's not the student. He also received the ACM CIIR 2024 Best Paper Runner-Up Award, and then a few other impact and Best Paper Awards from for the mid-teens and things like that. He has coordinated activities in several research projects in the EU and in Italy. He's a member of the editorial board of ACM TOEIS and a PC member of more conferences than I care to count. Other service contributions. He currently teaches information retrieval, surprisingly enough, in the computer science and AI master's degrees of the University of Pisa. Today, he's going to talk to us about efficient indexing with sparse representations of text. Please join me in welcoming Franco Maria to the CIIR talk.
Thank you for the kind introduction. And first of all, let me thank for inviting me to this talk series. I'm very honored and extremely happy to be here tonight, depending on where we are, discussing efficient indexing and retrieval with learned sparse representation of text. I should say this is, let's say, a presentation that summarizes, let's say, 2 years of activities in this specific topic. And first of all, just one moment. I cannot see you, but thanks a lot to all of you in the room for attending this talk. That's something I am very, I want to say before starting. And the 2 years of research we are going to see together are, let's say, the output of a great team of researchers and students. I want, first of all, to thank all of them because that is it's part of an incredible journey we did together with a lot of fun. The talk is about learned sparse representation. So let me give you a brief outline of this talk. In the beginning, we are discussing, learned representation of text. Then I'm going to discuss with you some challenges in retrieving with learned representation. And then you see some questions. Those are the questions we actually asked in this room together while brainstorming in the historical path I'm going to show you. So are inverted indexes dead? Can we learn from graph methods? Does this scale to massive data set? Does this scale to low resource devices? In the end, what's next? Because we have, let's say, a lot of questions still, as usual, still to be answered. So there is, let's say, plenty of possibilities to work in the future on this topic. Learned representations of text. We know from 2018, BERT shows that large language models heavily impacted, let's say, NLP and IR a bit later. Specifically, one line of research, you know very well, exploit such kind of models to encode in information retrieval, query, and documents into real valued vectors. Approximate KNN is, let's say, another field of research that has been heavily, let's say, linked to such kind of approach. And in 2018, indeed, such kind of new, let's say, possibility unlocked a new paradigm for query processing, because now it is, let's say, models, queries, and documents in this line, which is called representation-based techniques, representation-based methods, are encoded with an encoder, which is neural network, to produce, hello to all of you, to produce embeddings, okay? Embeddings for document, embedding for queries, and indeed, KNN is what is used after the encoding to build the final list of the result, to build the relevance score, which is basically dot product between the vectors. No? This new approach in query processing has been in one flavor done with dense representations, because we know that LLM in the beginning were used to encode documents and queries in two different flavors. On one side, we have single vectors dense encoders that, given a query or a document, produce one embedding for both of them. On the other side, people, specifically Khattab and Zahia in CIIR 2020, asked themselves, is it possible to go a bit down in the granularity? Instead of encoding one document or one query into a single vector, why don't we go one vector per token, no? With Colbert? And then using what they called length interaction, computing relevance with such kind of approach. So multi-vector on one side, single vector on the other side. And in the years after, literature shows that multi-vector provide improved effectiveness, because now we have several, let's say, embeddings for a specific document or query. So much more, let's say, fine-grained retrieval technique, but indeed the other side is larger document collection with higher retrieval time. I'm not going into such kind of line of literature, it's here just for completeness, but there is then a lot of work on top of Colbert for trying, let's say, to have better trade-offs, efficiency effect for efficiency effectiveness. This is for what regards the dense world, but indeed on the other side, information retrieval has a long tradition on the sparse world, no? So another line of research was indeed focusing on learned sparse representations of text. What is a sparse representation? Instead of mapping a query or a document into something which is hundreds of dimensions, like in the dense world, say, vector, here we have a sparse vector, thousands of dimensions with a lot of zeros. And the interesting part is that these sparse representations are grounded on the tokenizer, on the vocabulary. Specifically here we have an example. What shoes do most NBA players wear? And as you see, the representation are words with some, let's say, weights that are produced by the learned model. So from one side, one interesting, let's say, possibility that such kind of representation unlock is the fact that these kind of encoders are interpretable by design, because now we are able to look inside the representation. What are the dimensions, instead of having a latent n-dimensional space like in the dense world. Another very interesting part is that they actually, using expansion on the query and document side, they are very, very good in fighting the vocabulary mismatch. So they can be fine-tuned, so to expand the original document and query by including related terms, where related comes from the semantic. Here in the example again, you see the representation contain, for example, basketball, which is something not contained in the original query. For this reason, it has been shown that are highly effective for both in-domain and out-of-domain, in both in-domain and out-of-domain scenarios. Everything good up to now, no? Because we are very happy about this, but there is a problem. The problem is that such kind of techniques are not very well connected with the previous machinery we were using for retrieving with original text, with standard text, which are inverted indexes. Here, in the learned world, inverted indexes are no more efficient because indeed queries in the previous world were short. Here may not. Specifically, also if we consider the expansion mechanism we were discussing before, then also in the language we know that the words are distributed following a Zipfian distribution. Here there is no more Zipfian distribution, and this is something that impacts a lot the machinery, the inverted index machinery, because they have been designed exploiting evilly such kind of distribution. This is something that we were discussing a lot in the past years, and indeed the community, the information retrieval community, tried to overcome such kind of limitations. Specifically, we started using approximate nearest neighbors technique, specifically approximate because such methods allow to trade off the high cost of the exact search now in this world for efficiency, for gaining efficiency. On the other side, people, here an example, Lassans and others in CIIR 2022, were trying to overcome such a, let's say, problem on the learning side. They propose efficiency plate, which is a splayed model that has been trained to produce shorter queries and to basically translate the powerfulness of the expansion on the document level. This is a very interesting, let's say, technique, because having a short query allow to, let's say, gain time in the query processing without losing the power, the expressiveness provided by the expansion mechanism now on the document side. Several different, as you see, a big problem. In 2023, this is the historical evolution of the literature, the big NN at NeoRIPS introduced the challenge, introduced a sparse track to, let's say, facilitate research in this, let's say, incentivate and facilitate the research in such kind of problem, and with a lot of, let's say, surprise. At that time, I remember looking all together here while brainstorming, we understand that the two winning solution of this, let's say, track were graph-based methods, no? PyANN and GrassRMA, which are basically two sparse adaptation of HNSW, a very well-known graph-based method for doing KNN. So, in this, let's say, line, which is basically having a big problem with the previous machinery and then trying to adapt to a new world, the question that was in this room at that time was, are inverted index really dead? Because we are, let's say, efficiency guys from a lot of years, and indeed we worked a lot in inverted indexes. So we were asking ourselves, is it possible to somehow contribute again to a new machinery that indeed now works well with learned representation? Spoiler, no, they are not dead. And indeed, I'm now going to present you our answer to this specific problem, which is grounded on concentration of importance. Concentration of importance is a property we found in several learned representations, state-of-the-art, I would say, learned representation, SPLAID, efficient SPLAID, Unicoil T5, and others. Concentration of importance is a very interesting property in those representations that indeed shows that there is a non-homogeneous distribution of the L1 norm across different components, both on queries and document coordinates. Coordinates means dimensions of the sparse representation, just to avoid, let's say, terminology confusion. So basically, we discover that in this representation, the L1 norm in the vectors of documents and queries is concentrated into few components. This is plot here on the right, top right, shows these kind of properties. Basically, 80% of the L1 mass is within the 25% of the terms of both query side and document side. This was something very interesting to observe because the natural question that comes on the table at that time was, okay, but what do we need in order to, let's say, properly estimate now the dot product between the query and the document? And indeed, the property holds also on the dot product side. Few components are needed to properly estimate the dot product. Which means that now candidate documents can be identified with a reduced amount of components of the vector of the document and the vector of the query. You see on the right, bottom right, indeed, there is a plot that shows y-axis, the fraction of the inner product, by varying the top document coordinates with fixed top query coordinates, 3, 6, 9. And as you see, given a cut over the query, you still have more or less 90% of the dot product of the final dot product with more or less 50% of the terms of the documents. This is now extremely interesting because this is, let's say, the property, we call it concentration of importance, that now changes the scenario, because having this property allows us to redesign the overall machinery based on inverted indexes. This observation leads us to the introduction of what we call as CIIR. CIIR is a new inverted index-based machinery for retrieving efficiently with learned sparse representation. It's built on two data structures, an inverted index and the forward index. The forward index is basically a dictionary, okay? Doc ID, vector, full vector, let's say exact vector of documents. And this is used for exact dot product computation, okay? It's used only at the end of a, let's say, query processing algorithm I show you in a few slides. The inverted index is here used as a way to pinpoint documents to evaluate. And the fact that now we have concentration of importance allows us to easily exploit pruning techniques, okay? On one side, static pruning that indeed allows us to shorten posting list. On the other side, dynamic pruning, basically skipping documents that are unlikely to be relevant for a specific query term. So we start our let's say, overview of CIIR, of the inverted index of CIIR, by looking at static pruning. In the standard inverted index, static pruning allows to basically shorten posting list. Here is the same. We basically build the posting list for every component of the learned representation, of the sparse learned representation, for all, let's say, documents in our collection. Then what we did is to basically sort documents inside posting list and then prune at lambda entries. Lambda here is an hyperparameter which is then tuned during our experiments. Indeed, this allows to shorten every posting list by removing documents with, let's say, small component with a small weight for that specific component. On the other side, we can do now also query pruning, because concentration of importance also for queries, which means we prune the query to the first query cut, second hyperparameter, query cut components that are the ones that are basically the ones with higher score, no? Score associated with the terms. The two pruning, I already told it, are, let's say, grounded on the concentration of importance property, which holds both on the document and the query side. So now what we have is a pruned inverted index and something which also holds on the query level. But this is not enough, because still, if you go query processing on this kind of inverted index, you still need to pay a lot of time. What is doing in our seismic architecture, the inverted index, is the following. We introduce another layer on top of posting list, which is blocking. Blocking has a specific function. We group documents by similarity, okay? For every posting list, we produce beta block, third hyperparameter, per list. And these blocks are very interesting now, because now blocks contain similar documents, okay? Blocks, if you are interested and curious, are let's say, built using a shallow version, very, very fast version of k-means that actually group together inside the posting list similar document with, let's say, small overhead in terms of time during inverted index construction. And grouping is done by, let's say, by associating to centroids what actually maximize in terms of dot product. Okay, so we now have posting list, and inside posting list we have these blocks. The rationale of having blocks inside posting list that contain similar documents is that of trying to understand if a block can, let's say, contain interesting documents. If yes, I go inside. If no, I skip. Okay, that's why similarity, because this allows to skip blocks in case I know in some way someone tell me that this is something not indeed promising. How can I understand now if a block is promising or not? We introduce on top of the block what we called a summary. A summary is basically a vector, a d-dimensional vector, representing the documents inside the block. And this is meant to answer the question, do I really need to enter the block? Because if that block is not interesting, I can skip, okay? And the summary, to answer this question, we need to understand what is, let's say, the dot product I can achieve if I visit that specific block. For this reason, the summary contains, let's say, an upper bound of the full inner product I can achieve by visiting that specific block. So for every component, we basically keep the max of the I can observe in the documents of the block, and I store these as a specific value for that component in the summary vector, okay? But now your, let's say, comment can be, summaries cost a lot. And indeed, that's true. Because if you go with plain summaries on top of blocks, which are beta for every posting list, don't forget, the space grows significantly, okay? So space grows quickly with the block cardinality, which indeed has drawbacks in memory footprint, and also it's time consuming because I need to compute a lot of dot products also with summaries, which is an overhead, no, of query processing. We apply pruning also on the summary level. We just keep the top components that basically allows us to reach a lambda, an alpha mass fraction of the original summary vector. We have a vector which is basically characterized by a specific norm. We cut it up to a certain number of components that indeed reach an alpha fraction of the norm itself. So it's a specific part of the overall, the part that counts more to the dot product, okay? I just want the rationale is to, let's say, limit the growth in space while having a quite good approximation of the upper bound of the dot product I can achieve in that specific block. That's the reason. Then we also apply quantization on top of the summary just to keep summaries, let's say, limited in space. And this is now interesting because as an overall, we have posting list. Every posting list is statically pruned. There is also blocks on posting list grouping similar documents. On top of the block, there is a summary, which is now shortened to keep space limited, quantized to keep space limited, but it's still a good approximation of the possible dot product I can achieve for that specific block of similar documents. So the construction algorithm overall goes from, let's say, stage 1, which is the standard inverted index construction, to stage 2, which is pruning the list, to stage 3, which is now building blocks inside the posting list of similar documents, and then stage 4, which give a summary to every block inside the posting list. That's the final structure of our inverted index in Seismic. If you have questions, feel free to do it now at the end, the way you want. I'm open to all possible ways, okay? Query processing on top of the on top of Seismic is now, let's say, an adaptation of a term at a time algorithm, which is basically required on top of the query processing to basically compute the encoding of the query and then cut the query to the query cut number of terms I want to consider now in my query processing. Don't forget, query cut is a parameter and indeed identifies the terms of the query in the learned representation with higher weights, only the ones that I want to consider given concentration of importance. Then for each block in the inverted list, I go computing the dot product, the approximated dot product between the query and the summary of the block. And if the summary is promising, what does it mean the summary is promising? I go on the heap and I check on the heap what is the, let's say, the value of the document inside. There are some approximations here, but it's technical details. I just look at the heap and check whether I have space on one side or the score I'm computing with the approximated summary. It's somehow in the order of what I have inside the heap, which is the top K, no? If that's promising, I go inside the block and I compute the exact now inner product with the forward index, okay? I go in the forward index, I fetch the real vectors, and I compute the exact vectors for the documents to then do, in case they are okay, do the push on the heap. In case the approximated summary doesn't provide something interesting, I just skip and go to the next block. That's what indeed allows us with Seismic to achieve very good efficiency now, very good latency numbers, because we are able, with such kind of arrangement of the inverted index, to skip a lot of possible documents, okay, while keeping recall very high. I am going to show you a table in a while for that, okay? So forward index just come into the scene for computation of the exact dot product. Everything in inverted index is approximated just to skip the most I can, okay? Now, at that time, experiments also over the Big NN challenge, Sparse track, were done over MS Marco. Specifically, we include in this paper MS Marco v1, 8.8 million documents. And then we also tested out-of-domain evaluation on NQ, which is 2.7 million documents. And we employ in our experiments 3 different encoders: Splayed, efficient, which was state of the art at the time, efficient Splayed, which is, as you remember, the variant of Splayed that wants to target efficiency in the learning by shortening the query length, and Unicoil T5. Now, on the right, you see this table, which indeed reports the final performance of the 3 encoders provided in their original papers, and also a statistics of the average non-zero coordinates, both on document level and query level. Document level, central column; query level, right column. As you see, Splayed expand a lot the query, 43 non-zero coordinates on average, while efficient Splayed works a lot on this side by shortening queries to 6 terms and transferring the expansion work on the document side from 120 of Splayed to 180 of efficient Splayed. Unicoil is something which expand less, which is 68 over the document side, 6 terms over the query side. So our evaluation on the 3, using these 3 encoders, is done using mean query latency reported in microseconds, accuracy at 10. Here, accuracy is, let's say, an overload of recall, because we wanted to be clear that we are not measuring now recall with respect to human judged document. Here we are measuring recall with respect to closest points of a specific query. Okay, so we are not using human judged stuff. We just rely on distances, inner product of points in the representation. That's why we call it accuracy, to avoid confuse at that time the reviewer on the possible, let's say, meaning of the metric. And then also index size, so the final space required by the both the inverted index and the forward index. In terms of competitors, end of 2023, we had our Seismic, and we wanted to evaluate, which is written in Rust, and we wanted to evaluate it against GrassRMA and PyNN, which are the 2 winning solutions of the Big NN challenge, both written in C++. Then we also added 2 techniques: IOQP, which is an impact sorted inverted index, again written in Rust by Australian guys, Alistair and I don't remember the original author, but this group. Sparse IDF, which is an inverted index, again written in Rust, that exploit clustering for building internal posting list. So something smarter than a plain inverted index. Now I show you a very big table. I hope you are able to see it, because it can lead to very small, let's say, numbers. But this is something needed to have an overall of the performance. You see this table. On top, you see the combination encoder dataset, splayed MS Marco. On the left, you see the competitors, IOQP, Sparse IVF, which are two inverted index solutions, then the two graph-based HNSW variations on Sparse, Grass RMA and PNN, and then Seismic, bold line, okay? Splayed, so the table is, let's say, organized in different columns because every column is a specific accuracy level. 90%, 91, up to 97%, okay? So accuracy fixed, we check all the methods, the time needed by all the methods to guarantee such kind of accuracy, okay? And we measure mean query latency reported in microseconds. Okay, as you see, played over MS Marco, the two inverted index solution, first two rows, IOQP and Sparse IVF, are very slow, okay? The second one is faster, the first one is slower. Indeed, why? Because queries are very long. Remember the average number of terms. So inverted index here struggle, okay, in answering in a fast way. The two graphs are indeed faster, okay? And these results confirm what the Big NN challenge provided, specifically PNN outperform the Grass RMA solution, but now with Seismic inverted index-based solution, we are able to outperform the winner of the Big NN challenge from 2.6 times up to 3.5 times in, let's say, in terms of speed up in mean query latency, okay? So, super interesting result from our side. Now the next question is, what about efficiency plate? Because efficiency plate was designed to target efficiency on the inverted index. And indeed, this is now another interesting result, because if we consider efficiency plate on MS Marco, we see inverted index standard techniques doing much, much better, both IOQP and Sparse IVF at all accuracy levels. On the other side, shortening the query doesn't allow graph-based methods, both Grass RMA and PNN, third and fourth row, to be efficient as before. Why? Because few terms on the query level doesn't allow to identify on HNSW the right path that leads to a good, let's say, region of the space for fetching relevant result. And indeed, the two graph-based method here lose a lot in terms of their, let's say, retrieval time. Here, on this specific encoder, Seismic is more or less, provide more or less the same performance as before, same from more than 200 microseconds on the 90% of accuracy, up to 500 microseconds on the 97 level of accuracy, with interesting speedups over all of them. Same results are achieved. For let's say unicoil and splayed. So I'm not going let's say to comment them, also because from what I see I now have 20 minutes, which is more or less what I need to conclude. Same results achieved also on this side, but in the meanwhile, while developing Seismic, another strong team of researchers, Malia and others, were working on the same problem, proposing faster learned sparse retrieval with blocks max pruning, ACM CIIR 2024. So the next question for us was, how do we compare with respect to BMP, which is the method they propose? which were indeed contemporary. So we did the same comparison on MS Marco with, let's say, splayed embedding. And as you see, given same MRR in terms of effectiveness and same, let's say, space required for storing the indexes, we are still more or less 100 of magnitude, one order of magnitude more, let's say, better in terms of query mean query latency with respect to them, which is, let's say, for us, an interesting result achieved. In terms of index size and building time, we compared the index size and the index building time with all the competitors. And as you see, we let's say, confirmed some evidences in literature that are, first, graphs are very slow in terms of building time. As you see, graphs RMA and PyNN requires several, let's say, more minutes than the inverted index-based solution for building the data structure. Seismic here has the fastest building time, although we also do, let's say, a shallow k-means inside the building of the posting list. On the other hand, IOQP has the smallest size of the data structure, just because they exploit only an inverted index with no forward index. So they basically save space for storing only the posting list. On the other side, Seismic and the two graph-based solutions require storing also the forward index, which is more or less 4 gigabytes for MS Marco V1. So those are the sizes required. They are all more or less in the same range, from 5 to 10 gigabytes for the 4 competitors. Another interesting message that comes here is that we know that query expansion now improved the performance in the out-of-domain scenarios. No, what the expansion mechanism allows to basically keep accuracy high even on out-of-domain, and we observe the efficient displayed lesson teach us that indeed, if you want to keep high performance on out-of-domain, you need query expansion, but standard inverted index then struggle in answering with, let's say, small query latencies. Here, we show that indeed Seismic is not affected by query expansion. Why? Because there is concentration of importance that indeed work on shortening to the only terms that really counts in retrieval. No? So Seismic is not affected by query expansion overall. So extreme query expansion is possible, and that's an open question because it's something we indeed didn't target yet. How can we go? What is the limit in query expansion when coupled with such kind of efficient data structure for retrieval? That's, for us, an open question. Second main question that was in our mind, okay, but now we have an inverted index based machinery that works efficiently. But can we learn from graph? Because graphs were state-of-the-art just 1 month before. So can we learn something that indeed allows us to do even better with the inverted index? And indeed, we can learn a lot from graph-based method when paired with an inverted index strategy. Why? Because from an intuitive point of view, if you look at HNS-W, you have a hierarchy that indeed exploit a global locality of the points. No? You go to the ground level and then you search using and exploiting a global locality of points. In our solution, the inverted index exploit a per component locality. So what if we merge the two approaches? And here, another, let's say, result shows that if we merge something inverted index based, our approach, with something coming from graphs. And this is something, let's say, very basic in this solution. We just pre-computed, let's say, closest point with respect to a document, and we store it to enrich a possible solution coming from the inverted index. We can indeed go even better. And here we compare standard seismic machinery on inverted index with an evolution of seismic, we call it seismic wave, that exploit K documents pre-computed for every document of the collection to enrich a preliminary solution identified by the inverted index. By doing that, we grow in space now because we need to store candidates for every document, but we are now able to speed up from 2.2 times up to, 2.2 times the original latency provided by seismic, just because we are using the graph to exploit the global locality and store it with, let's say, the original machinery. The experimental evaluation here is done by bounding the available space, just because we want to be fair with competitors, with, let's say, the original seismic implementation. But now, at that time, we said, okay, now we have a combination. No? We added the graphs on top of, let's say, an inverted index-based strategy. Does this all machinery scale to massive data set? Because we are now still focusing on MS Markov V1, which is 9 million documents. What if we go to MS Markov V2, which is 150 million documents? Spoiler, yes, we can scale. And this is a third work that indeed shows that we can, using MS Markov V2, again, with splayed embeddings, with a fair comparison between seismic, both graph and non-graph, and HNSW, we are able to, let's say, always outperform a graph-based solution, HNSW, by margin, okay? We also show that indeed the graph-based solution is faster than the seismic plus graph is faster, always faster than the seismic original, with latencies on top of, let's say, MS Markov V2 that are order of from 1 millisecond up to 4 milliseconds to answer on top of 138 million documents. With a memory, with a space that grows at most 1.5 times the original seismic one and 2.2 times the original space required. Here we also compare, because now there is the question on the table, what about the building time? You use a graph, so you need to pre-compute, closest point for every document and then store. And indeed, we show that in terms of building time, HNSW and our seismic with graph are now comparable. We are, let's say, slower, but more or less same order in terms of hours required, while we have the same, let's say, required space in both the three solutions. Now, the fourth question is, in my opinion, one maybe the most interesting, because I was always, let's say, so the previous one is the first work in literature that indeed study the performance of retrieval on top of a quite big collection, which is MS Markov V2. Here, the question, does this scale to extremely low resource device, is another question we had in mind from several years. What if we move something which is, let's say, searching on top of learned representation to a very resource-constrained device? And the spoiler is, yes, this also scale to low-resource devices. In this work, we move retrieval from a standard cloud-based machine, which is in our case an Intel Xeon with 1 terabyte of RAM, cost order of 10K euro, with a lot of power consumed by the machine, to a Raspberry Pi 3B+, which is a super, let's say, cheap device with 1 GB of RAM, with very low parallelism, 4 cores, and very limited hardware acceleration, only for we have hardware acceleration only for floating point 32 numbers, okay? So we were, let's say, on the other side of the scenario. What if we go there? What happens? Because to the best of our knowledge, there is no study that indeed shows the performance, how retrieval behave in such scenarios. So the goal was to evaluate. Up to now, we were in the first study we studied retrieval phase. Okay, so what it means that indexes were built on a high-end machine, and then we move indexes on the Raspberry and we do retrieval on top of the machine, on top of the Raspberry. Vectors are converted to FP16 to reduce the memory overhead. So there are some, let's say, technological adjustment to allow the best possible performance. For example, assumed acceleration via on-the-fly conversion of the floating point numbers. Evaluation again, accuracy at 10 versus queries per second. And surprisingly, on the left, you see the query per second, now query per second, at different accuracy levels on a dense scenario, okay? This is a more, let's say, an extended study. We have sparse on the right, dense on the left. And as you see, on the dense scenario, we are able to achieve more than 100 queries per second at 99% of accuracy, even on a Raspberry Pi 3B Plus, which is super limited. On the right, you see the performance of Seismic. And again, Seismic on a Raspberry 3B Plus is able to, let's say, go even to perform even more than 300, let's say, queries per second, 98% of accuracy, which is, in our opinion, super interesting. For comparison, if you do the same, same methodology on our, let's say, server, we can achieve up to 8,700 queries per second and 99% of accuracy on Quora. So much more, let's say, queries per second. But indeed, the difference in terms of hardware are more than more justifies a lot of this, no? So I show you 4 questions with the answer we gave to those questions. And indeed, this is a story of 2 years of research that indeed lead us to, let's say, a software result, which is Tuscany. We are in Pisa. Pisa is in Tuscany, which is the region of central Italy. So we were, let's say, playing a bit with the word. We said, let's introduce Tuscany, which is a suite, our suite for efficient NN search. On the left, you see one graph-based library. We did it. It's Rust, written in Rust. It's Cannolo. Cannolo is built with researcher in mind, okay? Because everyone, if you want to use a graph-based index, you need to use FAIS, but FAIS is super engineered for production-oriented library. Here, we wanted to design something which is indeed usable by PhD student, by researcher, something which is easy to modify for prototyping ideas. We did this, and indeed we lead to something which is also faster than FAIS in terms of performance. There is a paper showing the comparison. And this is the first library that indeed allows you to build a graph index over dense and sparse. The sparse part is not covered by FAIS, okay? You can do sparse vector using the 2 winning solution of the Big NN challenge, as I told you before, or you can use Cannolo to do both dense and sparse variants. Super easy to install with pip, okay? Sorry. The second library is Seismic, only for an inverted index-based solution, only for sparse vectors, which is now fully available in the Hugging Face Center Transformer library, FlashReg, and also now, recently, OpenSearch, okay? Super easy to use also with Python APIs using pip install PySeismic LSR. Now there is the fifth question: what's next? No, because we need the questions because we want answers. No, and indeed this year we were focusing, we were coming back to the original query processing architecture. And we are not the first one working on this. In CIIR this year, there were, let's say, 3-4 papers working on inference-free encoders, because now if you look at this architecture, there is one bottleneck, which is query encoder, no? The encoding of the query before moving to KNN. We provided a solution, which is not the only one in the state of the art, that indeed allows to, let's say, remove the query encoding by computing fast lookup tables. For queries, we basically remove the contextualization and compute and pre-compute the score for every term, for every possible term of the query, and store them into lookup table. Now, given the query, I go in the lookup table, I fetch the weights, and I go to KNN directly without paying the neural network. This is indeed something that allows, that doesn't allow to fully exploit the contextualization mechanism of the neural network, but we show that we lose not so much while accelerating the query processing in an interesting way. So, in terms of what's next, for sure, there is the inference-free part, because in my opinion, we have a first contribution from many groups, from several groups, but there is this, let's say, trade-off in the contextualization, which is, in my opinion, not really fully explored. So we need to find a good trade-off. There is also one point which we are let's say investigating now. What does it mean? So we observed the concentration of importance as a property. We didn't understand why it's there. So a theoretical explanation and specifically understanding why it's there, it's the first step toward possible new encoders that do even better on the retrieval side. Then we have a question which is more general. Do we really need a quite complex machinery like Seismic? Because Seismic is for sure powerful, but indeed, and I'm concluding, it's indeed quite complex. Can we simplify it without losing performance? And still, there is this point on the interaction, the interplay between graphs and inverted indexes. We show they can be very good friends. We need to find a better way to exploit the powerfulness of the two worlds. With this in mind, I thank you all for attending. If there are questions, I'm more than happy to answer. Thank you for your attention.
Thank you, Franco Maria. Any questions locally? If you have a question remotely, please just raise your hand. Okay, well, I have a question.
Sure.
On the seismic, I guess you're calling it seismic work, if I understand the accuracy evaluation, it was basically saying how close are the top 10 to what was retrieved with a baseline system, right? So, but I know that pruning, almost any type of pruning is going to affect recall, because you're sort of taking low-scoring things and tossing them away in some level. I'm wondering if you ever did any work to explore going past 10, like what happens in the top 20 or the top 50 or the top 100, just to see when it starts to fail or how that's related to the value of lambda or things like that.
That's a super good and interesting question. Indeed, to be totally honest, no. But that's something we need to do. Thanks for your question. It's something we just focus on the top 10 because here, to be honest, also the literature focus on this. So we want to be one-to-one aligned with the methodology, but that's a super interesting question. Thanks for that.
Sure thing. Yeah, I think we all focus on the top 10 a lot, so it's not a surprise at all.
Yeah, no, but you are right. You are totally right. We need to go. We need to go deeper in the list and see where things are actually where we are doing worse. Let's say no, where things are let's say doing bad. Thanks.
Right. Perfect. So, Hamed, I see you have your hand up.
Yes. Thanks for an interesting talk. And sorry if you hear some noise here.
No problem.
I have a question, and it's kind of a more generic question. This and so all of these, if you answering, they were about just the retrieval model itself. I'm just wondering when we have retrieval as part of a bigger system, like for example, in a RAG setting, let's say, is in the simplest approach. Do these efficiency questions change? Or no, we should just say, hey, I don't care what's the downstream application that's using this retrieval model. I should just isolate retrieval and just focus on efficiency of retrieval model.
That's an interesting question because in a RAG scenario, for sure, if you go measuring the latency end-to-end, there is the generation part, which is indeed for sure dominating the overall. So RAG changes the scenario a bit. This is not a work focusing on such kind. We were basically focusing on standard, let's say, retrieval pipelines. But yes, in that specific scenario, maybe we need to revisit the way our questions there. Yes, I think so. I don't know if this answers your question, but for sure things changes in that part.
Yeah, thanks. Yeah, it answers, and I think it's a interesting question to think about what changes and how we should build these efficiency models, because efficiency of these end-to-end systems is not just about retrieval alone. Sometimes maybe we can say, hey, our retrieval can be a bit more expensive, but if I retrieve fewer documents, then the downstream LLM is going to process fewer documents, so that the whole thing would be more efficient. So
Sure.
It's
Sure.
kind of a
what comes into my mind is for sure the part about expansion. So having, let's say, an expansion mechanism that indeed is now not bounded by the performance of the system can indeed improve the quality of the top results you go to the LLM, or you can then work also on the number. No, you can reduce the number of documents provided by the LLM. So those are for sure two dimensions that are affected in the change of the architecture we are actually observing end to end.
Okay, thank you so much.
Yes, for example, our integration, we did the integration in FlashRag because because we observed that some RAG system indeed were using Sparse, but also there the exercise was to basically integrate without taking into account the generation part, just observing the improvement on the, let's say, local retrieval part, which is not the total story. Yes, thanks for the observation. It's a super interesting insight we need to work on.
Great. Thank you. Yeah, I think that we're over time, so I think we'll stop so people can get back to their real lives. So thank you once more.
Thank you all for attending.